Welcome, curious minds, to another deep dive. Today we're plunging into a world where AI isn't just writing articles or generating images, but truly becoming the ultimate co-pilot for developers.
Yeah, churning out code faster and more intelligently than ever before. We see models like GPT-4o, Mercury, Gemini. They're constantly pushing the boundaries.
Exactly. But what's really fascinating is how they're doing it and, whether open source AI can actually keep pace.
That's precisely the core question we're exploring today. I mean, these commercial models have set an incredibly high bar,
Right.
and it raises a critical challenge. Can open source alternatives not just compete, but maybe innovate in ways that push the entire field forward, especially for something as complex as code generation?
Well, that's our mission for this deep dive. We're unpacking a cutting-edge paper titled DiffuCoder, Understanding and Improving Mask Diffusion Models for Code Generation.
Solid, yeah.
Our goal is to peel back the layers and understand how a specific, pretty powerful type of AI model, a diffusion language model, is being custom tailored to get really good at writing code.
And the new innovations making it even better, yeah.
Right. And we'll explore those novel innovations too.
What's particularly insightful right from the start of this paper, I think, is the very nature of code generation itself. Traditional AI models often build things sequentially, word by word or token by token.
Like writing a sentence, basically.
Exactly. But writing code isn't always linear like that. It's often a non-sequential back and forth refinement process.
Okay.
Almost like sketching out an idea and then iteratively filling in details across the whole canvas, not just left to right.
I see. That inherent nonlinear characteristic is what makes diffusion models maybe intuitively well suited for code generation.
That's the idea. Finding an AI architecture that inherently thinks a bit more like a human developer might.
Okay. So the paper highlights that while commercial diffusion models like Mercury from Inception Labs and Gemini from DeepMind are indeed rivaling top autoregressive models for code, there's still a gap, right?
A significant one. It's been pretty unclear how open-source diffusion language models perform, partly because their training and inference mechanisms haven't been fully understood or, well, publicly interpreted.
Which brings us directly to the problem the DiffuCoder researchers set out to solve. Existing open-source efforts, like LIDA 1.5 and D1 or MIDA, they've only shown what the researchers call marginal gains.
Yeah, not huge leaps, or, and this is crucial, they rely heavily on something called semi-autoregressive decoding.
Okay, semi-autoregressive decoding. That sounds technical. What exactly is that, and why is it a problem here?
Well, think of it like this. Semi-autoregressive decoding is basically trying to force a naturally non-sequential process, like diffusion, into a more sequential box.
Right.
These models generate code in small, fixed-size blocks, one after the other, even when the diffusion model itself is capable of a more holistic, kind of global planning approach.
So it's like step by step when it could be seeing the bigger picture.
Precisely. The paper points out that this fundamentally deviates from the global planning nature of diffusion. It's like trying to fill in a complex puzzle piece by piece, only ever looking at the immediately adjacent empty space when you could be looking at the whole picture at once.
Gotcha. So it's a workaround that kind of limits the true power of diffusion. What's DiffuCoder's strategy to overcome this then?
Right. The researchers behind DiffuCoder aim to address these limitations with a sort of two-pronged strategy. First, they wanted to gain a much deeper insight into how diffusion language models actually decode understanding their inherent thinking patterns, if you like.
Okay.
Second, they're establishing a new, truly diffusion-native reinforcement learning methodology. So teaching the model in a way that respects and actually enhances its unique non-sequential capabilities.
Which leads us neatly to DiffuCoder's key contributions. And there are some significant breakthroughs here, it seems. First, they've introduced a foundational 7 billion parameter diffusion language model, DiffuCoder, specifically designed for code generation. Why is just having a new base model such an important contribution even before the novel training stuff?
Well, it's not just another standalone model. It's designed as a crucial building block, a robust, specialized platform upon which future, even more powerful and truly diffusion-native AI training methods can be built.
So it's a solid foundation, a reliable test bed for their later innovations.
Exactly.
That makes perfect sense. And then, to really understand these models, they developed some clever analytical tools, didn't they?
Yes, and what's fascinating here is how they approached understanding the decoding patterns. They introduced these new local and global ARness metrics.
ARness, meaning how autoregressive or sequential the decoding process is.
Precisely. These metrics help demystify how these dLLMs decode and, crucially, how those patterns change during different training stages.
Okay, like what did they find?
For example, their analysis reveals that using higher sampling temperatures, think of it as letting the model be a bit more creative or less constrained, actually encourages more parallel, non-autoregressive generation.
That's a really crucial insight. It sounds like they're mapping out the personality of these models.
Kinda, yeah. And then, to actually teach them to leverage that non-sequential nature, they designed this innovative reinforcement learning algorithm, coupled-GRPO.
Okay, tell us more about coupled-GRPO.
This is where their truly diffusion-native approach really shines. Coupled-GRPO is specifically tailored for diffusion language models. And crucially, it avoids that semi-autoregressive decoding entirely.
How?
It uses a novel coupled sampling scheme. It's a clever way to get more efficient and accurate estimates for fine-tuning the model's decision-making strategy, the policy gradient estimation.
So it's not just a theoretical improvement on paper, it delivers actual results.
Absolutely. Its effectiveness is proven experimentally. Coupled-GRPO significantly boosts DiffuCoder's performance. It improved its EvalPlus score by 4.4%, with training on only 21,000 samples.
Wow, that's efficient.
It really demonstrates the power of reinforcement learning when it's truly aligned with diffusion principles, instead of, forcing the model into that sequential box.
Okay, this is fascinating. Let's maybe unpack some of the foundational building blocks that make DiffuCoder tick. Starting with masked diffusion models themselves. How would you describe these, especially for text and code?
Sure. So at its core, a diffusion model works in two phases. Imagine you have a perfectly clear image, or, in this case, a piece of clean code.
Yeah.
The forward process gradually corrupts that data. It adds more and more fuzz or noise until it's completely obscured, like turning a clear photo into pure static.
By making it messy. And then the magic happens.
Exactly. The backward process models how to reverse that fuzzing. It learns, step by step, how to denoise that corrupted data to reconstruct the original clear image or code.
And for text, which is discrete words or tokens, not pixels, how did that work?
Good question. For discrete data like text, they use discrete diffusion models. These models define that forward fuzzing process using probabilities, basically deciding which tokens to corrupt at each step.
And the paper mentions a special mask token for code.
Yes, that's a special case called absorbing discrete diffusion. It uses a unique mask token. This lets the model learn by intentionally masking out parts of the code.
Like hiding bits.
Exactly, hiding bits. And then it learns to fill in the blanks or denoise those mask sections. The model's learning goal is basically to get really good at predicting the original code. Technically, it minimizes the negative log likelihood via something called the evidence lower bound, or ELBO.
ELBO. Okay, so ELBO is just the mathematical framework guiding it to make the best possible guesses about the original code.
That's a good way to put it. It pushes the model to make accurate predictions, even with all that noise or masking.
Okay, so if that's how diffusion models work, how do you apply something like reinforcement learning to what sounds like a denoising process? That seems like a jump.
It is, and that's where the concept of a Markov decision process, or MDP, becomes crucial. Other research, like papers on DDPO and DPPO, cleverly reinterpreted the denoising diffusion process as a Markov decision process.
Framing it as a game the AI plays.
Essentially, yes. A game where the AI makes decisions at each step to reach the best possible outcome, which is the clean code.
And like any game, you have components. How does the MDP break down here for code generation?
Right. For an MDP, you need states, actions, transitions, and rewards. States. That's the current condition, the time step in the process, and the noisy code itself. What it looks like right now. Actions. That's the denoised output the model produces at that step, its best guess. Transition probabilities, how the state changes after an action, how the code evolves, and crucially, a reward function. This tells the model if it's doing well.
Okay, and the reward. When does it get that?
Importantly, for this kind of masked diffusion, the reward isn't given at every tiny step. It's given at the very final denoising step, based on the quality of the entire piece of generated code.
So it's all about the final result.
Exactly. It's judged on the completed code.
Got it. And then to actually implement the reinforcement learning for this MDP game, they use something called Group Relative Policy Optimization, or GRPO.
Yes, GRPO. It's a method that simplifies another popular RL algorithm called PPO. PPO often needs a separate value function, like another AI, just to estimate how good each state is, which can be slow.
Right. So how does GRPO simplify things?
GRPO takes a different approach. It samples a group of different code outputs the model generates at a given moment.
A batch of attempts.
Yeah. And then it calculates a relative advantage for each output in that group. It compares how good one output's reward is compared to the average reward of the whole group.
So it learns which of its attempts were better than average within that batch.
Precisely. By viewing the diffusion process as an MDP, GRPO can be applied. It uses this group-based comparison to refine the model's policy, its strategy for generating code guiding it towards better outcomes without needing that complex value function.
Okay, so we've laid the groundwork, understanding the why behind diffusion models for code and how RL can be applied via MDPs and GRPO. Now, the moment of truth. How did the DiffuCoder team actually build this thing? What makes its training process special?
Right. So DiffuCoder is built on a strong base model, as we mentioned, trained on a huge code corpus. But the real innovation is in its meticulous multi-stage training pipeline.
Multi-stage. Okay.
First, there's an adaptation pre-training phase. This is similar to how models like Dream are trained, kind of getting the model warmed up and ready for the specific task of code generation.
Then comes mid-training. The paper calls it an annealing phase. Sounds like a careful, gradual step.
Yeah, it acts as a bridge, smoothly connecting that initial pre-training and the crucial later post-training stages. It helps ensure a stable learning progression. This technique was also found effective by OpenCoder.
Makes sense. And after mid-training?
Then comes instruction tuning. This is where they specifically enhanced the model's ability to follow explicit instructions or prompts. They used a large data set for this, around 436,000 samples from OpenCoder.
How did they do the instruction tuning? Any special techniques?
Yes, they used careful strategies like classifier-free guidance, SFT, and flexible padding to really optimize how the model understands and acts on those prompts.
Okay, and finally for post-training, they bring in their novel coupled-GRPO method, which we'll dive into more deeply. This stage is specifically designed to further boost code generation, especially that pass-at-one score, right?
Exactly. That pass-at-one score is a key metric. Does the code work perfectly on the first try? Coupled-GRPO targets that directly.
And they tested it rigorously.
Oh yeah. They put DiffuCoder through its paces using a diverse set of Python coding benchmarks. Human Eval, MBPP, EvalPlus, Big Code Bench, covering both code completion and instruction following tasks.
And the results? Table 4 in the paper looked pretty promising.
It is. After being continually trained on 130 billion code tokens, DiffuCoder achieves performance pretty much on par with other strong autoregressive code LLMs like Qwen 2.5 Coder and OpenCoder. That's a big deal for a diffusion model.
But there was a catch, wasn't there?
Yeah.
Regarding instruction tuning.
Yes, a crucial observation. Most diffusion language models, including DiffuCoder before the GRPO step, showed only marginal improvement from instruction tuning compared to AR models like Qwen 2.5 Coder plus SFT, which saw significant gains from it.
Ah, okay. So that highlights the exact gap that their novel coupled GRPO method aims to fill. It suggests that just instruction tuning isn't enough. You need a diffusion-native approach to RL.
Precisely. It underscores why their method is so important.
This naturally leads us to how DiffuCoder actually thinks and decodes code. We talked about those AR-ness metrics, local and global autoregressiveness. A purely AR model would hit 100% on both, always decoding left to right.
Right. But here's where it gets really interesting. As Figure 3 in the paper shows, these diffusion language models do not always decode in a purely AR manner. Meaning a significant chunk of tokens are recovered from positions that are neither the leftmost masked token nor the very next token in sequence.
Wow. So they have a much more flexible, non-sequential decoding order.
Exactly. It's like they're not just filling in the blanks strictly left to right. They might identify multiple parts of the puzzle simultaneously and start tackling them in parallel.
But the paper also notes they still lean towards AR behavior.
They do, which suggests there's still an inherent sequential structure in text data that even these models pick up on. And models adapted from AR LLMs tend to inherit stronger AR-ness.
Okay, and this flexibility, it has practical implications, right? Like for speed?
Absolutely. This lower AR-ness directly translates to more parallel generation opportunities.
Like a team working on different parts of a problem at once, instead of one person doing it step by step.
That's a great analogy. And practically, it means fewer diffusion steps are needed, which means faster generation. Figure 11 in the paper specifically shows that their coupled GRPO training actually improves DiffuCoder's parallelism.
Interesting.
And higher sampling temperatures lead to even less AR-ness, which means less of a performance hit when you try to speed up generation by using fewer steps.
They also mentioned something about an entropy sink analysis. Sounded subtle but important.
Yeah, that was about how some baseline methods for estimating token probabilities can be biased. They found these methods sometimes update early tokens more aggressively, leading to uneven learning. It's a small detail, but optimizing that is crucial for stable training.
Okay, now let's really get into the heart of their innovation. Coupled GRPO. You mentioned RL and GRPO work well for AR models, but applying them to dLLMs was tricky. Why was that?
The main hurdle was getting a stable estimate of a score for each token in the generated sequence. You need that score to guide the reinforcement learning. Current mass diffusion models often rely on Monte Carlo sampling to estimate these scores.
Monte Carlo, like random sampling.
Essentially, yes. But it can introduce a lot of noise and significant overhead, making the GRPO training unstable and slow.
And the researchers found issues with the existing baseline methods trying to solve this.
They did. Older methods like D1 tried to simplify things by masking all completion tokens and doing a single forward pass. But the paper argues this baseline is biased.
Also,
Those high entropy tokens, often appearing earlier in a sequence, get updated more aggressively. It creates an unbalanced learning process. They also found that masking condition tokens, which some methods do for diversity, didn't reliably improve the reward for code generation tests in their experiments. Figure 7 shows that.
okay, so this is where coupled GRPO comes in to fix these bias and inefficiency issues. How does it work its magic?
This is a really clever part. Coupled GRPO is specifically designed to reduce that variance, that noise, while still being efficient. The core mechanism is this novel coupled sampling scheme.
Coupled sampling.
Instead of just taking purely random samples during training, which can be noisy, they generate antithetic pairs.
Antithetic pairs. What does that mean in practice? How does it help?
Okay, imagine you're trying to measure something precisely, but your measurements wobble a bit due to random noise. If you take two opposite or balancing measurements,
Like a plus and a minus that average out.
sort of. In this case, if the process samples a certain diffusion time step t and a mask pattern m, it also deterministically creates a counterpart, like 1t, 1m. By pairing these opposite samples, the random noise tends to cancel itself out when you average their results.
Ah, okay, so the wobbles cancel out, leading to a more stable, less noisy estimate of how well the model is doing.
Exactly. It makes the training signal much cleaner and more reliable.
And they proved this mathematically. It wasn't just an intuition.
Correct. Appendix A.4.2 has the rigorous proof. It shows that this coupled estimator is unbiased, meaning it gives the right answer on average, and crucially, it has lower variance than standard Monte Carlo.
Lower variance, so less noise.
And the proof shows this isn't just likely, it's a mathematical certainty because the covariance between those paired samples is guaranteed to be negative. This leads to a precise reduction in variance, significantly improving training stability and accuracy.
That's really elegant. And the practical results?
They were strong. DiffuCoder applied coupled GRPO by training on just 21,000 hard samples from the AceCoder 87K dataset. These were samples specifically chosen because models struggled with them: low average pass rates, high variance.
So they focused the training where it mattered most.
Right. And they used a weighted reward function prioritizing code correctness heavily, 2.0x weight for passing tests, 0.5x for formatting.
And even with just one epoch?
Even with just one epoch of this specialized training, DiffuCoder instructs performance kept improving. It really showcases how effective RL can be when it's truly aligned with diffusion principles. Figure 7 also shows visually how the reward curves for coupled GRPO are consistently better than the baseline methods.
Okay, so to wrap this incredible work into the broader context, let's briefly touch on related work. Text diffusion models have come a long way, right?
Yeah, from continuous ideas to discrete models for text. We've seen scaling efforts like Diffulama, Elotade, DreamIt. Those were among the first open source dLLMs to really get competitive.
And they're hybrids too.
Approaches like lock diffusion, and even multimodal models combining text with vision. It's a busy field.
And on the reinforcement learning side?
RL has definitely boosted AR models for things like math and code, but applying it effectively to diffusion models was the tricky part. Previous attempts like D1 and MMATO often fell back on that block diffusion decoding we talked about.
The semi-auto-regressive workaround.
Exactly. It wasn't truly diffusion-native. DiffuCoder, with coupled GRPO, really distinguishes itself here. It unleashes RL's power in a way that truly respects and enhances the diffusion model's unique, non-sequential strengths. it kind of sets a new standard.
What an incredible journey into the heart of DiffuCoder. We've really peeled back the layers from the basic idea of masked diffusion right through to the genius of coupled-GRPO.
Yeah, it's clear this work really pushes the envelope for AI code generation. It moves us closer to models that think in a more parallel, non-autoregressive way.
This deep dive really hammers home that advancing AI isn't just about throwing more data or bigger models at the problem.
Not at all. It requires a deep understanding of the fundamental principles and, some clever algorithmic innovations like we saw here. It's about smarter training that actually leverages the unique strengths of these newer architectures.
Allowing AI to think in maybe more human-like, iterative, and holistic ways. So what does this all mean for you listening in? If models can generate code, or really any kind of text, not just sequentially word by word, but through this flexible parallel refinement, what new creative ways could non-autoregressive generation change how we interact with AI, beyond just getting code faster?
It opens up some interesting possibilities.
Yeah, what possibilities open up when AI thinks less like a linear writer and maybe more like a holistic problem solver? We'll leave you with that thought to ponder.